Go ahead, Nico.
Okay, let's start. Good morning. I am Nikos, as Stelios said, from EuroCC Greece, that we have a strong collaboration with HPC Cyprus. And today we will discuss how we can do some basic machine learning calculations for structured data sets using the Julia language. We will run our notebook on Google Colab. I will now share the link for the notebook. It is also on our GitHub page. I think probably you'll have the page, but I am sharing directly the notebook in the chat. I think it is a good idea to run in parallel, I mean, I will present some commands and you can run them as well in order to get more familiar with the environment, language, commands, and everything. Okay, I don't know if you received the...
I'm putting the link on the webpage of the event now.
Okay. If you received the notebook, we start from installing Julia. It is the first of all, we change the runtime type and the hardware accelerator to GPU. We go here, runtime, change runtime type, and select Julia and GPU accelerator. And then we run the first cell. We simply press this button here or click inside and press Shift plus Enter. And this will take 1 minute or 2, and it will install Julia. After installing Julia, we refresh the page, and we are ready to run the commands. If you face any problems, please let me know. I will wait for a couple of minutes to install Julia, and we can start then with the commands. Does anybody have the link and try to run the first cell here?
It's running.
Okay, thanks. Yes, it will take some time because it has been installed Julia. Julia is not native in Colab, but we can run this by running these commands. I have also some references for the default notebook on how to run Julia on Colab, and with the packages, we will use various packages. While we are waiting, I can say that Julia is somehow new language. It is some years now, but okay, it's not very well known. It is a just-in-time compilation language, which is distinguished for a high-performance compiler. It is a new language developed for machine learning, scientific computing, and data science, developed at MIT with exceptionally fast compiler. The speed is similar to C, which is not very, this does not happen very often in just-in-time compilation languages. We can also easily run parallel commands and CUDA. We will see some basic syntax today. So it is appropriate for high performance computing as well, because as you know, our project is on high performance computing, AI, and high performance data analytics. I don't know if your notebooks are also ready. If Julia is installed, then you simply refresh the page after the installation, and you start running the commands. We start with here, check version info.
Has anyone finished the installation? Yes. Okay.
It says that it's not authored by Google or something, but still runs anyway.
Did you make a copy in your Google?
Oh, I should. Okay, hold on.
Yes, you can make a save a copy in Drive. Sorry, I forgot to mention this. File, you go to File, save a copy in Drive. So if you are connected with your Gmail account, then you can save it in your Google Drive, and you can run it on your, let's say, local directory, cloud again, but your own directory. Yes, so we can do this. And then you can change it, because it is, Google copies everything from the initial notebook, and you can change it, you can put more commands, etc. Anybody else that ran the first cell? No. I will, because if we don't finish this, then we cannot continue. So if anybody wants to ask something, please go ahead and let me know.
I'm just rerunning the commands in the copy.
Okay, okay, nice, okay. Okay, I will continue. If I say again that when the installation finishes, then you reload the page with Control plus R or the refresh button of your browser. You refresh the page and then you can start running the commands. So we start with version info with Shift Enter or this button here, and we get the version, the information about the Julia version. Currently, the latest is 1.8.2, and we can see that the number of threads is equal to 2 because Colab gives us two threads. Okay, the important is that it gives us a GPU, so okay, this is fine. Then we continue with installing the packages. We use this syntax, import pkg. Pkg is the umbrella package for installing the other packages. And we can add a specific package by writing pkg.add. For example, here CSV in quotes. The data, we will use CSV, data frames, linear algebra, statistics, pyplot, statspace, XGBoost, decision tree, file input output, random, and CUDA. This is similar to pip install in Python or conda install. So this command will install the packages. If I run this, then it will start installing all the packages. Now I have installed everything, so probably it will do nothing, or yes, no changes, etc. But at your screen, it should start installing. Also, we will use the pyplot package. It is for plots. There is a native plot package in Julia, but it has some problems running on Colab. At least I faced some problems. So we will use pyplot, which is actually matplotlib from Python. We can import matplotlib and use the same syntax as in Python within Julia, the same syntax without no difference. And as soon as we install the packages, then we start with importing the packages. The syntax is using and the name of the package. We can use more than one with commas. Using is equivalent to import in Python. Okay, so I use all the packages I installed, and then I use pyplot, which is a matplotlib, and also I select some specific methods like plot, bar, scatter, legend, show, title, and hist. This is I write this in order to avoid writing plt.plot, plt.scatter, etc. It is faster. I import the functions in an initial cell here, so I have them imported and I can use them directly. And then I do a sample plot with nothing, just to check that everything works well. Afterwards, I go to this cell. We always have at the left side the table of contents, so we can see where we are. And I will use CUDA now, using CUDA. This is an interface for kublas and all the related commands, which is really, personally, I find this really helpful. Because it is a very simple syntax. We can use CUDA with the same the same linear algebra commands as the basic syntax. So I run using CUDA, and then CUDA allows scalar false, because if by accident I send scalar computation to CUDA, it will be really slow. So I prevent this with this command, CUDA allows scalar false. And then I start with a CUDA array. As you know, in order to run CUDA, we should send everything to the GPU RAM. So this command is a Julia command for initializing a random matrix, and then I wrap it with this CU command, and this is now a CUDA array. This is a CUDA array with random numbers, a CU array. You see here the type and the data type float 32, single precision. And this is now on GPU. If it is a CU array, this is on GPU. So we can run everything on the GPU. I say again, if you face any problems, please interrupt me and ask me for the installation or the syntax or anything. Okay, I continue now with some simple commands to get familiar with Julia. If I want to initiate a random array, I write x equals rand. I put here the type, the data type I want to use. I use float 32, which is we use very often in GPUs. I could also try float 64 or int 64 to prepare random integers. So if I run this, I get a random array. If I run again, I get another one. And similarly, I start a random vector here. I initiate a random vector with dimensions now 1, 199. So this is, the previous was a column vector. This is a row vector. Now, if I want to develop a matrix containing each column will be the first vector, the x vector, raised to the power of alpha vector, of a vector. I do not need to use a loop, a for loop to do this. I simply write x dot raised to the power of alpha of a. So my x vector is 10 by 1, my alpha vector is 1 by 199, and this will result in a matrix of 10 by 199. So this raised everything to the power of alpha directly.
Excuse me.
Yes.
The randomly generated numbers are always between 0 and 1?
Yes, the default, this rand here is from a uniform distribution with limits 0 and 1. So the default is this, but we can use other distributions as well. We can use Gaussian, exponential, whatever we like. Also, we can use a specific ring for the, if we wanted, it's time to present, sorry. I don't remember the command. There is a command for a specific ring if we want to, it's time to prepare a random vector with the same numbers for reproducibility purposes. But if we don't want to be this in the range 0 and 1, we can, for example, if we want this to be from -5 to 5, we can multiply this by 10 and subtract 5, So this, oops, here I need to write this. Sorry, 10 times 0. Okay. Why? Dot time. When I multiply a vector with a number, this is with the command dot times, or if I subtract a number from a vector, it is dot minus 5. So if I prepare this for 1000 numbers and I plot a histogram of X, then I get this. So this vector now comprises values from -5 up to 5. Okay, so initially the random vector is from 0 to 1, but I can transform it to any range I want.
Okay, thank you.
Okay, thank you for the question. And as we said, oops, write again here then. And as I said, we raise this vector to a power of alpha easily. Why? Yes, because now this is negative, so it cannot be raised to a fractional power. So I have this. This command is really fast, as we said, because it is a very simple syntax to write, a mathematical syntax. And also it is very fast because this is vectorized. Whenever I use this dot operator, all the computations are vectorized, are running in a vectorized manner, which is very good for our processors. So these commands are really fast. Okay, similarly, I can produce a range, not with random number storage now, but with a range with numbers in specific positions. So this is similar to Python as well. I can produce a range from 0 to 99 with a length of 100. And then I collect the range. The range is an object in Julia. It is a range object, but I can convert it to a vector by using this command, collect. So I write collect outside the range. And then, okay, I can run it one by one to be more clear. If I write range here, I get this. It is a range. It's not a vector, a mathematical object. But if I write this, then now with collect, this is a vector. But this is 100 by 1. If I want 1 by 100, I get the transpose of the vector with this symbol here. And then I get this 1 by 100. Then, but this is a vector of float 64 by default. So I can easily cast this vector to int 64 by writing int 64 the data type dot because this is a vector and I want to cast everything. Dot parenthesis collect range blah blah blah. I get my final vector. Now let's go to plots. Let's say I want to plot the sinus function. I write plot. I use a pyplot syntax now, which is the same exactly as in Python. So I use plot sinus dot. I write the range here, 0 with step 0.1 up to 2 times pi. And I also add a label, and I tell Julia to put the legend and to show the plot. I think this is not necessary as we have only one plot. So just plot and legend. And I get my plot. Here I continue with matrices. I will now prepare a larger matrix with a random matrix with dimensions 1000 by 10,000. I can use this underscore letter here, character here, if I want to distinguish the thousands. So I have x 1000 times 10,000 and the y 10,000 times 1000. I run this and I get my random matrix. Now, if I multiply x times y with the well-known multiplication symbol, it is a really simple syntax. Now, let's say I want to assess the performance of the multiplication. So I will count the time it will take. I write this T1 equals now, it gets the current timestamp, and T2 equals now, and I subtract the T2 minus T1. And I run the multiplication for 10 times in order to have a more statistically reliable result. I get this value here. It takes 5.8 seconds. It is important to note here that the first time I run a function, actually this times symbol here, this star here, is a function which multiplies two numbers or two matrices. Each time I run for a first time a function, it is compiled at this time. So it has some overheads. It will be a bit slower the first run. So we have to remember this, especially when we assess performance. If we assess performance, we first write the command without outside the loop, and then I run the loop. Okay, and now I go to CUDA. I want to see how much time it will take to run in CUDA, the same matrix multiplication. So I convert my arrays to CUDA arrays by writing CU of x. I prepare a new matrix here, CUX equals CU of x. So this sends everything to the GPU, and the same for y. CUX equals CU of x and CU of y. And I have this random matrix now on GPU. Again, I run. Now I can multiply two matrices on my GPU with the same command, exactly the same command, star times. Nothing less, nothing more. I mean, it is very simple. And now I ran this on my GPU, and it took 13 milliseconds. And previously, it was 4,900 milliseconds. So I compare the scale up. It is T2 minus T1 over T2C on CUDA, this number here, minus T1C. So I have like 400 times faster computation with the same syntax. Personally, I find this really helpful. Okay, we continue now with the for loops. I can start for loop. I write this for I equals 1 up to 100,000. If I in this range, one with step 1000 up to 100,000. Then this Papaki symbol here. So I, comma, SQRT of I. This is equivalent to print in Python. Print in Julia is print as well, but if I want to change line, either I should write the /n operator or I write print line I, comma, s, comma, an empty space, comma, sqrt of I. So I can try both. This is with print. It prints the I and the square root of I. And I can also run the show command. The show command is faster when I do experiments in real time. Show command is faster if I want to see something, how it is running. So I run this with show now. Interestingly, I can convert this loop, this for loop, in a parallel loop simply by writing the @threads command here. If I write Papaki threads for the same loop, then I run this in parallel. Okay, now I have only 2 threads, but if I have more, this is really helpful. I mean, it's really easy to develop a parallel loop. So I can run this @threads again for I equals 1 up to 100,000, blah blah blah, and I print these the same numbers as before, plus my thread ID. I can get on the fly the thread ID, which thread I am running, by writing this command here, thread ID, parenthesis, parenthesis. And I run this, and you will note that it is everywhere too. Why? It should be 1, 2, 1, 2. Ah, it happened because it is if I in 100, if I write here, for example, 1001, and I run again, I get again 2. I don't know why this is happening. The first thread ID is only 1, and all the rest are 2. I'm trying to figure out why this is happening. Let's put yes. Okay, perhaps the other thread is for some is working on some other computation, so it use only 2. If you run this on your laptop, this will change here each time you I changes. Okay, so we can have this parallel loop, and with this command threads dot number of threads, I get the number of threads. Now we continue with some linear algebra. Let's say I want to, let's start with a random matrix math from matrix math equals rand, type float 32, dimensions 10,000 by 10. I get my random matrix here, and then I repeat this matrix 3 times. So I concatenate 3 matrices here with this simple command. This is how I can combine arrays. I have an array math, and then I add with 10 columns, and then I add 10 more columns, which is again math times 2, and 10 more columns, which is math times minus 3. So now I have a matrix with 30 columns, but it is we can say that all the columns from 11 to 30 are linear combination with the columns from 1 to 10. So the rank of this matrix will be 10, which is rational. And let's say that I have that this is a given matrix. Now it is artificially generated, but in machine learning, especially when I do feature selection, the first step, my opinion, is to get a matrix, an input matrix with linearly independent features. So in order to do this, I can do one of the ways to do this. I can do a QR factorization. I have also the rank, so I get the first k pivoting the indices of the first k pivoting vectors by writing this idx equals sort of q. Q is the QR factorization dot p. P are the indices sorted by sorted by the non-linear. The first 10 are the linear independent indices. So I get IDX this. Interestingly, it selected the last 10 columns, although I started with the first 10, but okay, it's the same. I mean, in terms of linear dependence, it is the same because it is everything the same times a number. And now the rank of my matrix with the columns IDX is 10. So everything is fine. I check out if I am correct. Now I prepare, we continue with some other commands. Apart from linear algebra, we can very easily develop functions, methods to do an operation. XX equals 1, parenthesis 10,3. This is a matrix with ones, with dimensions 10 rows and 3 columns. And then if I write sinus dot parenthesis XX, I get the sinus function for all the elements of X. Then I can develop a function. I can write f of X equals tan H, the hyperbolic tangent, of sinus of exponential function of X. You may notice that I write a function the same way as I write in mathematics. This is really simple. And this can be as complex as I want. Okay, of course, I can write more complex functions with more steps, but if I want to write a mathematical function, this is really simple. And then I get again a random matrix, and I write f dot math, and I apply this function to each element of my matrix. This is again vectorized, so it is very fast as it is parallelized in the internally in our processor. Then if I have a good array, CU math equals CU of math, and I can compute the function of each element of this CUDA array now with the same syntax again, f dot CU math. Does somebody want to ask something up to here? Okay. So I continue with a more complex function like this. Function, I write function. Now I define my function. Function g of x, and I start with this syntax and end with the end keyword. and I write v equals sum of x, so this function will get a vector, and k equals the logarithm of the absolute of v plus 1, because if v has negative vectors, I should put them I should use the absolute values, and then I plus 1 because near 0 is in minus infinity. And I return k. Okay. Okay, and I run this function for many times for some random numbers, for a random array. The length of the array varies. So you see here, I start in NN range, which is from 1 with step 100 up to 1000. And I will keep the average of all iterations in this vector, which I initiate with zeros with length n. And okay, I do this, a k number, I start with the iterator, k equals 0. And for n in nn, okay, for this iterator n in this range, I start a vector mean equal to nothing. This brackets here initiates a vector, an empty vector, and then I can populate this vector during a for loop or whatever. I can add elements there with this push command here. This is similar to append in Python, but this is for vector, for everything, even for vectors with numbers or strings or everything. And so in the inner loop, for 1 up to 10, I produce a random matrix, but with dimensions n, comma n, which n varies. And I push in this vector mean, the average, the mean of the matrix. Okay, and what I do here, I add 1 to my external iterator k, and then the mean all of k equals the mean of the vector mean. Okay, I mean, I did this mean number, this averaging of the matrix 10 times in order to have a statistical significance. And afterwards, I put the mean of the means in the vec mean. Okay. Okay, I present this in order to be more familiar with the syntax. Okay, so that's why it's not something really interesting. But I can see also that the mean stabilizes after 100 iterations. Before it is not very robust, it can be high. Okay, I continue now, as we have already seen some basic commands and how to do CUDA and multi-threading on with Julia. Okay, now we continue with machine learning. We will see today regression, decision trees, and we will build very fast our own random forest by using only a decision tree. Okay, I started by generating some data. I use artificial data. I use a matrix XX equals rand with dimensions 100,000 and 10 columns. Okay, and I have this matrix here. And then I assume here, that my target variable, y, equals to the summation of the sinus of x, the summation of the sinus of x. This keyword dims equals to is like axis. In Python, it is the summation is being performed on the columns, on the axis too. And I add there a random noise. I add a random noise because I don't want to have a very clear relationship among X and Y, but I want to use a random noise as well. So I add a random vector with a length the size of X, 1 minus 1.5, 1/2, because as we said, the random vector is from uniform distribution from 0 to 1, and so I want to have fluctuations. This is actually the error of this will be the error of the noise, the noise of my observations, and I want to have fluctuations on the noise. So I mean positive and negative, and average 0. So I do this with this by subtracting 1.5, 1/2. And then I divide all this noise with 2, because I don't want to have a very big noise. Okay, so I compute this, my X, my Y vector, and I can compute some weights A, alpha, such that if I multiply X times A, I get Y. Actually, this is the solution of a linear system, a tall linear system. It's not square, so I use least squares, and I do this with this backslash operator here. This is from MATLAB, actually, similar to MATLAB and Octave. So I write this keyword at time, alpha equals X backslash Y. I get the regression weights, let's say, okay, the solution of the linear system. And then I plot alpha, I plot the weights, and I get this figure here. I would expect that the weights should be around 1. Okay, because actually not exactly closed 1, because I have 2 things that differentiate this, the sinus and the noise. We will see this later. Now I do the same on CUDA. Okay, I run this with CUX. It equals CU of X and CUY equals CU of Y. And because CUDA does not have CUBLAS, does not have least squares, a function to solve linear systems, I use generalized least squares. My matrix X is a full column rank, so I can multiply the transpose of X times X, and I solve for the transpose of X times Y. This will return the same weights. And I compute the time. You may see here that this takes only 2 milliseconds, while this took 10 milliseconds, so it is 5 times faster. But okay, my matrix is still not so big. But again, we have a scale up in the solution of the system as well. As you notice, it is we can run everything very simply, either in CUDA or on multi-threading. Okay. What I have to do, of course, is because AA is a CUDA array, a CU array, you see here. I have to convert it if I want to do more computations later, or to plot this or something else. I convert this to a CPU array now with this command, A equals vector of A. Okay, and I have the weights back on my regular RAM. And then I plot I do a bar plot by using this command, bar. This is for the legend, string of 1 up to 10, and the A are the weights. The weights I computed. You may see that they are all around 0.9 something. Now, I predict using these weights. The prediction matrix will be X times A. Okay. So the prediction will be this. And I do a scatter plot among the prediction and the actual values. Y was my target variable and pred is the prediction. And as a title, I use the correlation, the Pearson correlation among the prediction and the Y. So I get an image of this, which is expected. I have a very good correlation, but with a bandwidth of errors here, and this is because of the noise. The one thing is because of the noise, and the other thing is because I used the linear model, although my actual relationship was non-linear. Remember, Y was the summation of the sinus of X. So this is another source of errors, and this is very important in machine learning to distinguish always the noise from the signal. I mean, an error might not be an error, a noise, it might be an inability to capture the correct signal. Okay, I do some very fast error analysis. I compute my errors, which are the Y minus my prediction. And I plot the histogram of errors. You see, I have a good histogram, okay, but it is a bit skewed to the positive values. So, I mean, okay, it is like this distribution of errors ideally is a Gaussian with 0 mean. Okay, this is close, but not exactly. And then I scatter plot the errors versus target. This ideally should be totally random. Here I have some a pattern for higher values of Y. I have lower errors, negative errors, and for lower values of Y, I have positive errors. So this is not very good. They compute the correlation of the Y and the error is minus 14. That's why the decreasing pattern. Okay, this is not very bad. It is actually in the range of the. This can happen by chance. If I compute the correlation of two random vectors, I can get a Pearson correlation like this. But okay, perhaps we could investigate this more. Okay, so then I can sort my errors. I use this command, sort perm. I permute the indices of my vector such that I have a sorted vector. So this returns the indices. Okay, and I don't use all because I have 100,000 indices, and I don't want to plot 100,000. I want to plot a few, but to get the pattern, and I get this. This is really good. This is sorry, the previous was good. This is, I mean, we do this plotting the sorted errors in order to assess any patterns in my errors. We can see here some fat, a fat tail in the lower errors. So this is not very good. But sorry, I think I forgot something. Just a moment. Where are these? Sorry, I forgot to run some to run because I went before and I went after. I will start a few cells above. I will continue. I go, if you run with me, go to regression, predict, and then here to add nonlinear terms. That's why I had this nonlinear pattern and I was. But okay, it is useful now, I'm thinking, because we saw that by using linear model, we got these nonlinear patterns in the error. Let's now use a nonlinear model. Let's now use the weights like this. So if I add some nonlinear terms like x squared and x to the power of 3, then I use a polynomial model to simulate my y. Okay, and I compute the weights again with the same command. If I plot the weights, they are, I get this pattern. You see, if I compute the mean values of errors of the weights in the range 11 to 20, it is close to 0, and in the range 21 to 30 is close to minus 0.14. Actually, these terms here are the Taylor's expansion coefficients, because I simulated now the sinus with a polynomial. Okay, so I think I am correct. And then again, like in linear regression, if I predict, I get a better pattern, a better accuracy. You see now, the histogram of errors now is random. This is amazing. This is really good in machine learning, and I think it's a good idea to do this error analysis. The scatter plot is more random. Okay, the correlation is again 0.18, but as we said, this can happen by chance. But if I plot my errors, now I get a straight line indicating the random pattern. And again, I can predict for out of sample observations. I produce a new matrix X test with random numbers. Again, I raise this to the power of 2 and 3 times alpha. And I have now an accuracy, a Pearson correlation of 0.9999, etc. Why this? Because now in the test set, I did not add a signal. This is a technique we use when we want to assess a machine learning model. We add a signal in the train, we add a noise in the train set, and we use a test set without noise. If this approximates my test set well, then I have a good model. So, I mean, this is another way to verify my model. Okay, what I do here. Yes, this we did this before. This is for the train. This is for the yes, I think these cells are just copy of the previous. Okay, so we continue now with decision trees and the random forests. We just saw how to run regression models, linear and non-linear models, very easily and very fastly, both in GPUs and on CPUs. Now we will train a decision tree and a random forest. Okay, we will train random forest from scratch. I mentioned it. I mean, with our own code, without the package. Let's say that I have this function. I have some observations, 1000 observations, which is a random vector. And then a dependent variable which has this pattern. It's here 0, here in this range 1, here 0, 1, etc. Okay, so I want a tree to approximate this. I build a decision tree classifier very easily. I use a model equals decision tree classifier with max depth 100, decision tree fit, model X and Y, and then I print my tree, decision tree dot print tree, gives these results. So I have when feature arena less than 0.499 here. If feature arena greater than 0.92 here, etc. Blah blah blah. All the rules of the tree. And now I predict. I populate a new random vector X test, and I plot my X, my Y, my X test, and the prediction directly in the plot. Okay, this is fast. Prediction of the model and the test set. Okay, so I can see that I have a very good tree because the prediction is equal to the observation. Now that was a simple example to present the syntax of decision trees. But now let's say that I have a random vector, a random matrix with 10 variables and 10,000 observations. And my actual relationship among X and Y is X over 10 to the power of 2 times sinus of X. Okay, it's a nonlinear relationship. And I add a noise as before in my Y. You can try some various noise factors here, etc., or another function, or a real world data set. You can import an existing data set. Okay, if I scatter now the X and Y, I get this image, which actually is like a noisy signal, very noisy signal. I cannot get a clear image because I have 10 variables affecting Y, so I can understand nothing. Now, if I do linear regression for this problem, if I solve the system with the commands we said before, I get this pattern here. I get this pattern here, which I have only a correlation among the prediction and the signal and the target 0.3, which is very low. So linear model cannot do a lot here. Then let's say that I build a decision tree regression like before, a single tree now. Okay, if I build a single tree like we said before with a maximum depth of 1000, I fit the model, I predict, and I plot, then I get a better accuracy. I have a Pearson correlation of 0.64 now. Okay, so we are going well. If I print the model now, okay, I get this print result. Okay, it's a bit more complex than before, you see. And let's say now I want to train a random forest, a forest of trees, of random trees. What is the basic idea behind random forests? Is that I select randomly a portion of my data set, some of the rows of my samples and some of the columns randomly. And I build a tree there. I do this many, many times and I average the results. So simple, okay? I can do this very easily. Julia, I keep a model all vector. Here I initiate, as we said, with brackets, an empty vector, which I will populate later. I populate a I random column null. Here I will put, here, this will be a vector of vectors. I will put here the columns, the indices of the columns I used to train each one of my trees. I need to keep this information because later on when I will predict, I want to use it. I put a number of trees, percentage of column and percentage of row, and I do this in a for loop. Here I generate a random vector with random indices for my columns, and the same for my rows. And I train here a model I with input dx of, with indices I random row and I random column. The part of my input matrix I use to train this particular tree. And I save my model I by pushing this in model all. Okay, I run this for 100 trees and I get everything. And then I predict. As now I have model all, I have all my models. And as I have I, R, call all, I have the indices of the columns I used to train. So I predict for everything and I average the predictions, as we said. So now I have an accuracy of 0.97 instead of 0.64. Okay, it is quite enhanced. I do this for the test set as well. I have a lower accuracy in the test set. This is 0.97 in the test set, 0.92. So perhaps I have an overfitting there. Perhaps I try something different. Different, what I mean, different hyperparameters. For example, how many columns I use to train, how many rows I use to train, and how many trees. I can optimize this with a hyperparameter tuning algorithm. But okay, in any case, it is better than one tree. And finally, we will see how I can build a random forest in parallel. Okay, I use again the same code as before, exactly the same. The only difference is that now, because I want to do this in parallel, okay, in order to get faster, because with
Nico, we have a question.
Yes, sorry, yes.
Okay, so I was just thinking that, so in this case, because sometimes back I realized that for the random forest, it cannot extrapolate the data. So for example, if you just have the test set is out of range of the train set. So I don't know if it's going to replicate here that if you are going to test with a test set that is going to be outside the range of the training, what would be the accuracy? I'm just thinking.
Yes, this is very important and very, very important. I agree with you. We should always check this. Personally, I do when I start a machine learning project, I do some descriptive statistics and I compute the ranges of the train and the ranges of the test set, and I see if they are the same, and also the distributions. Not only the range, the minimum and the maximum, but also the quantiles should be the same ideally, or similar. Here I am quite confident that the range are similar because my test set, where it is, here I have a test set which is 10 times a random matrix of observations and variables. So 10 times rand will be in the range of 0.1. And the train set was with the same command, 10 again times rand obs, vars. So I am quite confident that because I have many values, I am quite confident that this will be in the same range. Perhaps 1 point or 2, I mean a few, will be outside the range, but not. This will not be a very big problem. But we can try this actually. Now I'm thinking if I used here 10 times rand, but 20 times rand in the test set. As you said, the performance is almost zero because half of my data set is outside the range. Yes, so I agree with you. Always we should check this. If my test set,
there should be work on how to use this algorithm to extrapolate the data, because if that's the case, then I don't know. I'm just thinking that maybe there should be work to allow this decision tree algorithm, the three algorithms like XGBoost and random forest to extrapolate the data. I'm just thinking if there's a work outside there. I don't know.
Yes, we can actually, we cannot extrapolate. If we have noisy data sets, we cannot, any algorithm we can use. Only for a few, we can get a trend only for a few points outside our range, like 5% outside the range, but not a lot. Even if we use random forest, even if we use XGBoost, neural networks, whatever, we can never extrapolate. A lot. Okay, a few we can do. But again, with sophisticated methods and etc. But it is very risky. When we extrapolate, it is really risky. Okay, so I will, we were here on how to build a random forest in parallel. As we said, we described how we build this model in sequentially with a for loop, but one of the powerful aspects of random forests is that I can, if I have many processors, one processor can build one tree because it is totally independent, one tree from another. So I can build a random forest in parallel. In order to do this, the only change I do is that I pre-allocate now my vector of models, by using this command here. I pre-allocate the vector. I use vector of decision tree regression undefined with length number of trees. So each one of my trees will be pushed in this vector. Not push now, I will use equal because I have pre-allocate the locations in my RAM. So model all of I now equals model of I. You see, previously I had push model all comma model I because I could do this because it was sequential. I built the first tree, I built the second tree, etc. Now because it is in parallel, if I do this, perhaps at some cases it's not thread safe. I mean, one thread could try to push a tree in my model all and another thread to do the same, and perhaps we could have a crash. So in order to build this in parallel, I pre-allocate. Okay, now it will not be very faster, but if I have, for example, a processor with 40 threads, then this will be many times faster. Not 40, but perhaps 30 or 20. Okay, I plot also the vector of the columns here. And my models, I print the first model, which has 1,123 leaves and depth 18, and the second model with depth 19. Okay, you see, I just check what the model all has now. And again, as before, I predict using each one of the models. Decision tree dot predict model all of I, comma, my random, my input matrix with columns, the I are called the columns I use to train, and I average the results. And I see similar results with previously for the training test set. I mean, this parallel random forest did not increase performance, accuracy, but it increased the performance. Okay. Basically, that's all from my side. I want to We discussed today some basic syntax of Julia language, and we saw how very easily we can use CUDA. We can transfer our arrays on the GPU. We used plots with matplotlib with the same library like in Python. We do some basic linear algebra computations. Linear regression, decision trees, and random forests, and also how we can train a random forest in parallel. Okay, we have a couple of minutes. We can discuss something. You find something interesting or you want to ask something, please go ahead.
Okay, so what I would like to say is primarily thank you, Nikos, for the session. Okay, so this is just an introductory session. If you look at our previous events, which are online, let me find the previous ones. I think we had more advanced sessions that Nikos gave.
Yes.
Where was that one exactly? So if you search on the website, our advanced training events of 2021, there's a session there that Nikos gave. I also believe you gave something in the previous intermediate session. Yeah. So you also had an intermediate training event in June of 2022. So you can find further sessions that Nikos gave, so more advanced to this, most likely. So you can find those online on the website. It's the intermediate session of 2022. Okay. Also in the advanced one. Okay. So did you give one in the beginner one also? Let me see.
Mm-hmm.
So again, all our material is online. No. Okay. So these two that I said, there's other sessions from Nikos that you can look at.
Thanks.
Okay. Thank you, Nico. I know you have a meeting you need to prepare for.
Okay. Thank you very much. I hope you enjoyed the session, and if you want to ask something, you can do it also by email or send Stelio any questions.
Okay.
Or
Thank you,
me,
Nico.
whatever. Yes.
Everyone, we're taking a break now. We come back in 25 minutes with the next session, which is from Valeria. So introduction to data sciences, time series this time. So we begin at 10:15, so make sure that you're back a couple of minutes earlier. Okay. All right. Thank you, everyone. Thank you, Nico.
Thank you. Bye-bye.
Bye.